For our final project for ABE 423, we decided to do a bioreactor modeling and scale-up procedure. The basic design of the Matlab code for this project is to take the substrates and put them into two different environments. The first environment is a feed batch reactor in which all of the nutrients are put in at the beginning and no more are added. The second is a flow reactor, which will continuously change over time. The final portion is going to be maximize and find the most efficient conditions for the feed batch bioreactor. The overall design of the system is to run 3 different modules to scale up a bioreactor. The first module is going to deal with the continuous flow rate reactor.
Continuous flow bioreactors are able to maintain steady-state operation through a continual input of nutrients and excretion of waste products. The flow bioreactor design considerations have been studied extensively, and equations governing their overall operation have been developed. A research team led by M.I. Nelson came up with the equations that we will use for our model. The change in substrate over time is a function of properties such as concentration of delivered nutrients, specific growth rate of the cell, and bioreactor volume. The cell concentration depends on growth and death rate as well as physical properties of the bioreactor. Product formation is dependent on cell concentration and the specific product formation rate. The first module works by taking inputs provided by the user and solving the differential equations associated with the flow reactor kinetics. The program ends by outputting graphs that show the cell, product, and substrate concentrations over time.
Module 2 consists of the fed batch reactor design. Fed batch reactors analyzes reaction kinetics and chemical equilibrium through a mass balance. A fed batch reactor differs from a continuous flow reactor in the sense that specific reactants are added to the system, allowing for a reaction to occur rather than a continuous introduction of reactants to a system over a period of time. In a fed batch reactor, ideal conditions are assumed. Therefore, mixing prevents concentration gradients as reaction concentrations decrease and product concentrations increase over time. This bioreactor modeled cell metabolism. Quantification and analysis of the metabolic pathways within a cell involves a series of chemical transformations. There are 2 main categories associated with cell metabolism: catabolism and anabolism. Catabolism involves the breakdown of organic matter, whereas anabolism uses energy to synthesize components of cells such as proteins and nucleic acids. This model focuses on anabolism, more specifically glycolysis, which is a metabolic pathway that transforms glucose into pyruvate. Glycolysis under anaerobic conditions was analyzed rather than aerobic conditions because of the greater reaction efficiency when oxygen is not present. This is explained by the Pasteur effect, which notes that the rate of glycolysis under anaerobic conditions is higher than under aerobic conditions because carbohydrate consumption is 7 times higher under anaerobic conditions. Since the program is analyzing a fed batch reactor, initial concentrations of the reactants are introduced into the system in order to start the process. To account for this, the program allows for user input of the initial concentrations of glucose, ATP, and pyruvate. The reason that the initial concentration of pyruvate needs to be known is so that the system will account for the amount of pyruvate already present by negating it from the amount actually produced by the system. There are several initial conditions that are considered constants in the system because based upon previous studies, the amounts indicated in the program account for native growth conditions within cells. The fed batch reactor models glucose being transformed into each of its products. Glucose is first converted into glucose 6-phosphate by this reaction rate, shown here. Glucose 6-phosphate's concentration is shown by this equation right here. As glucose 6-phosphate is converted into fructose 6-phosphate by this reaction rate, it is then shown by this concentration right here. However, glucose 6-phosphate is also converted into 6-phosphogluconate, which is shown by the reaction rate right here. Once that is converted, fructose 6-phosphate is converted into fructose 1,6-phosphate, and the reaction rate of that conversion is shown right here. Fructose 1,6-phosphate's concentration equation is shown right here. When fructose 1,6-phosphate is converted into pyruvate, the reaction rate is shown here, and pyruvate's concentration is shown here. Glycolysis requires energy in order for the process to work. ADP is converted into ATP right here. The reaction rate of this conversion is shown right here. ATP's concentration is shown right here. This is a positive feedback loop into ATP, which is converted back into ADP. This reaction rate is shown right here. ADP's concentration is then showed here. An additional reaction is when 2-ADP is converted into AMP. The reaction rate is shown here, and AMP's concentration is shown here. However, when 2-ADP is converted into AMP, an additional ATP is a product. This ATP can also be a positive feedback loop back into this reaction and produce ADP. So the entire process of glycolysis is in a positive feedback loop. So overall, these are the underlying equations to Module 2 that will then be illustrated in the program later on.
The final additional module that is used is the bioreactor scale-up for the feed batch bioreactor. This is governed by a few equations and is able to maximize the volume while requiring the least amount of power input into the system. This module receives an input of the max pyruvate concentration from Module 2 so that it can determine the overall yield. This module starts by making assumptions about the conditions that the reactor is run in. First, the density and kinematic viscosity of the solution is inputted for the user. This data is selected from previous experiments and is required for the power equation. The module requires 3 inputs from the user. The first is the diameter of the mixing impeller. This is required in meters. The next is the speed of the impeller, which the user is allowed to leave as variable number if they choose. The final input is the volume of the bioreactor, which is given in cubic meters, as this is a large-scale process. This input is also able to be modeled as variable. Since the code is supposed to maximize the bioreactor, a few assumptions and calculations are made ahead of time. The first being that the shape of the bioreactor is a cylinder, and that the height is equal to the diameter, which is the most efficient design. The first calculation that is run through in Module 3 is the Reynolds number of the system. This is given by the top equation. This is given as the diameter squared times the impeller speed times the density, all divided by the viscosity. The system then determines if it is laminar or turbulent, and then models the system with different selections of impellers such as a paddle, a Russian turbine, and as an ideal turbulent system. Once the power number is calculated, the power consumed is calculated by the lower equation and outputted to the user. The system will also take the variable conditions and model them graphically so that the user is able to determine which design is most efficient. Since increasing the volume increases the power consumption by the square of the ratio of the diameters, the program is able to tell the user which is the most effective volume and speed of the impeller that should be used. This is the end of Module 3. To demonstrate our Matlab, we're going to walk you through an example. To call up the actual program, you're going to type out Bioreactor and hit Enter. From here, an input window is going to show up.
For the first module, which models the continuous flow reactor, we need to input the cell doubling time and the rate of product formation. For the cell doubling time, we'll put 12 hours, which is a standard value, as well as the 0.003 for the rate of product formation. The next dialog box will have us input bioreactor physical characteristics. They include the flow rate, the volume of the bioreactor, and the concentration of substrate entering with incoming flow. The figure that comes out from this module will tell us the substrate concentration, the cell concentration, and the product concentration against time. And as we can see, eventually our continuous flow reactor will reach a steady state of approximately 500 hours. Also on the main Matlab screen, it will tell us the substrate consumed over the entire operation of the flow reactor, as well as the grams of product produced.
The next input dialog box to come up is going to illustrate Module 2, which is glycolysis. There are 3 input values that we need to enter. The first one is glucose, which we are going to enter as 12 millimolar, because this is a standard value. ATP will be entered as 2.1 millimolar, and pyruvate will be entered as 0.1 millimolar, both being standard values. 2 plots will come up. The first one is going to be concentration versus time. This is going to show the concentration of the 7 main molecules that are involved in glycolysis. The second plot is going to show your reaction rates of the 8 reaction rates I previously showed you in the PowerPoint. And then in the main command window, you're going to see the maximum concentration of pyruvate. This is going to be 4.0684 millimolar, which is then going to be fed into Module 3.
In addition to the plot, the other input window for the bioreactor will show up. This requires 3 different inputs from the user. The first one is, what is the speed of the impeller? If they choose to have variable, they'll put 0 in for these. For the one that we're running right now, we will have both the speed of the impeller and the volume of the bioreactor be variable. Since the diameter of the impeller needs to be known, they need to input 1 in meters, since we will be using 0.2, which is a common value. When this information is inputted, 2 different graphs will show up. The first one is the impeller designs based upon the power consumption that they have. This one is shown in a different window as well. In the other window, the impeller design as well as the volume versus the dimensionless power increase factor are shown here. It can be seen that as the volume increases, it exponentially increases in power consumption. The final plot is going to be the volume versus the amount of pyruvate formed. Since in the example only both being variable was modeled, there's a couple other options that can be done. The first that we'll try is when one of the variables is known. In this case, we will do the speed of the impeller. We will set it as 1 rotation per second, which is equal to 60 rotations per minute. When this is entered, we will see 2 graphs that show up. The first graph is the dimensionless power increase factor versus the volume in cubic meters, and once again the volume versus the amount of product produced. In the Matlab screen, we will see that the Reynolds number is displayed, which is very, very low, so the system would want to increase its speed, and then the other output is the amount of power needed to run this system, which is also very, very low. The final scenario is when the speed of the impeller, as well as the volume of the bioreactor, is known. For this case, let's set the speed of the impeller to be 3, the volume of the bioreactor to be 4 cubic meters, and the diameter of the impeller to be 3.5, so this will be a large system. When inputted, we find out that the Reynolds number is over 2100, which makes it turbulent, as well as we see the power needed to run this in watts. This concludes the tutorial on the scale-up from substrates all the way to a large-scale process of a bioreactor. Thank you very much.